wabarakatuh, and very good evening. Alhamdulillah, today we are again virtually meeting in a coffee talk session, which is sharing knowledge session. So today we honored that we have Dr. Ibrahim Sulaiman, our former postdoc staff, is now working as an international lecturer at UUM. So he will sharing with us in one of his topic or one of his recent study, which is in conjugate gradient method. So before we start, let us recite our Fatiha. Okay, Dr. Ibrahim, you still cannot open the slide?
No, already open. I will share now. Just 1 minute.
Okay, try to share it.
Okay.
Do you have a problem to share the slide?
Yeah, it's a bit loading, but
You can share with me, then I will share it for you.
okay.
You can share the slide by WhatsApp. Then I can help you to share in the screen.
Okay.
So for your information, Dr. Ibrahim, we will record this session.
Okay.
And you may have 30 minutes to present. And then after that, it depends on Q&A, if there is a Q&A.
I should share through WhatsApp?
Check.
Did I share through WhatsApp?
Let me check. You share it through WhatsApp.
Okay.
No, I didn't get it.
No, I said I was asking, should I share it through WhatsApp?
No, you can share it with me. I will share it for you.
Okay.
Because you're having a problem to share it now, right?
Yeah.
So you can send to me privately, and then I will share it for you.
Okay. Thanks. I already sent to you. Doctor, you received?
Yes, I already received it. Now I'm sharing it. Okay, can you see?
Yeah.
Okay. Okay, without further ado, I will welcome I welcome Dr. Ibrahim Sulaiman to start the presentation. Okay, Doctor, you may start now.
Okay. Assalamualaikum warahmatullahi wabarakatuh, and a very good afternoon to everyone. My name is Dr. Ibrahim Mohammed Sulaiman, former postdoctoral candidate in Faculty of FIK, and now working as international senior lecturer in School of Quantitative Science, Universiti Sultan, Malaysia. My area of specialization is conjugate gradient method and fuzzy nonlinear problem. But I focus on conjugate gradient method because of currently there are vast application in conjugate gradient method, and numerous researches are being carried out about the conjugate gradient method presently. If you can check on a daily basis, there are different approach used to solve an optimization method using the conjugate gradient method. As FIK is concerned, throughout the research is being carried out on conjugate gradient method or optimization method. All these researches are focused on solving unconstrained optimization problem. Yeah, so far there are no problems, there are no researches and carried out in UNISA on maybe the constraint problem or solving nonlinear equation using the conjugate gradient method. But currently, one of the vast area that has been gaining a lot of attention is has to do with applying the conjugate gradient method to solving nonlinear problem. So a lot of attention now has been diverted to solving nonlinear problems. So on a daily basis, you can check online. You will meet a lot of researches, daily researchers working on this. And if you're working in this field, one or two other, you can get an email from maybe people interested in this area on possible collaboration. So I will be presenting on application of conjugate gradient method to solving either unconstrained optimization problem or nonlinear problem. So the outline, these are the outline of the presentation. So we start by introduction. Okay, introduction. Optimization, it's one of the efficient, conjugate gradient method is one of the efficient methods used to solving unconstrained optimization problem in addition to nonlinear problem. You'll be given a function f of x. We seek to evaluate, to look for the value of x for which the function f of x is equal to 0. In this case, we are talking of nonlinear equation. This is not an unconstrained optimization problem. If it's an unconstrained optimization problem, we'll be talking about minimization of the problem. But I want to discuss about the nonlinear problem because current researches are mostly centered around applying the conjugate gradient method to solving nonlinear problem. And the conjugate gradient method are classified into, we have different classes of conjugate gradient method. The first class is the main conjugate gradient method. Then we have other classes such as the hybrid conjugate gradient method. We have the three-term conjugate gradient method. We have the spectrum conjugate gradient method. All these methods are modification of the classical conjugate gradient method. So you're trying to solve a function given f of s is equal to 0. No, the first slide, Doctor. Given a function f of x is equal to 0, you're trying to look for the value of x for which the function is equal to 0. So solution of x is the root of equation 1. So for problem, it's known as the root finding or the zero finding problem. There are two important classes. We have the singular nonlinear equation, which is one unknown, where f is a function from R to R, from real number to real number, and solution is the scalar x for which f of x is equal to 0. So system of n nonlinear equation is in the unknown, where f is a function from Rn to Rn. Next slide. So we have the following from our previous knowledge. We have type of equation. We have the simultaneous linear equation, and we have the one linear or quadratic. We have the simultaneous linear equation where we have, again, one of the linear on quadratic equation. So but our target, the next slide. No, before this. Next. No. That I'm on the third slide now. Third slide. No, next, before this. Sorry, doctor, I think I can share.
Share?
Yeah, I think I can share now.
Okay, please. So I'm stop sharing, eh?
Yeah. Sorry, I'm joining with the laptop.
So is it okay?
Yeah, I think.
So you are sharing now?
Yes.
Are you sharing now?
Yeah, I just connected using the laptop.
So you have a two account now.
Yeah. So I think I'll sign out from one. Once I sign in from this, I'll sign out from.
Still not appear here.
Huh?
It still not appear on the screen. Have you shared it?
Is it okay?
Yes, yes. So are you going to start from the third slide, right?
Okay.
Okay, that's fine. So you just change to presentation mode.
I change to
Presentation slide or presentation mode. Change to slideshow, please.
okay. Is it okay?
Okay, okay. Okay, you may proceed.
Okay, so okay, we are talking about nonlinear function. You're trying to solve a function given f of x is equal to 0. You're trying to look for the root of the function, where you're looking for the solution of x, which is the root of equation 1. So for problem, it's known as the root finding. We have problems trying to solve a function f of x is equal to 0. It's a root finding or the zero finding methods. So two important classes. We have two important classes used to solve the given function f of x is equal to 0. We have the singular linear equation, which is one of unknown, where the function is from Rn to Rn, which is set of real number. So the solution is a scalar. The solution to this problem is a scalar for which the function f of x is equal to 0. While system of n nonlinear equation is unknown, where you have the function going from Rn to Rn. From Rn to Rn. So we have the following from our previous knowledge. You can solve problem using simultaneous linear equation, or you can consider one of the problem which is on linear or quadratic nonlinear equation. The title of this presentation is going to be on conjugate gradient method and its application for solving nonlinear equation. As I have in my previous explanation, currently a lot of research has been carried out on conjugate gradient method. We have a lot of students, most of the students precisely working on under Prof. Mustafa, try to use the conjugate gradient method to solve unconstrained optimization methods, unconstrained optimization problems. But currently, a lot of researchers are working on derivative approach. You have a conjugate gradient method. For example,
Dr. Ibrahim,
yeah,
you are not sharing now?
yeah, I'm sharing. It's going to appear now. Okay, I want to use this. Okay. Can you see?
It's just a white monitor.
Is it okay, doctor?
Is it overleaf?
Hello?
Hello. Oh, we cannot see anything on the overleaf screen. No text on the overleaf. Okay, we can see it now. We can see it now, so you may start, Dr. Ibrahim.
Hello?
Yes, we can see it now. You may proceed. Yes, we can see it now. So you may proceed.
Okay. Okay, so I want to use this, I was explaining, this is one of the paper on three-term conjugate gradient method for optimization problem with application to COVID-19 model and robotic and motion control. If you can see, most of the research is carried out in UNISA and on conjugate gradient method for solving unconstrained optimization problem with application to regression analysis. So a lot of students try to, for regression analysis, you can just consider any type of data, being it road accident, being it marriage. You can, when you have a data that you can have maybe an X or Y axis. If you have the X and Y axis, you can parameterize the data to obtain a regression model. Then you can use the unconstrained optimization method, the proposed method, to solve that regression model, and you can compare your method with maybe existing method. But currently, a lot of researches has been done on various applications of the conjugate gradient method. One of the current approach, one of the current application in which a conjugate gradient method can be applied is solving robotic arm problem of motion control. This is something that has to be related to engineering. So that is why papers in this area, whereby if your method can be applied, you propose a method and you are able to prove the global convergence or the local convergence of the proposed method, yeah, it's okay. But one of the interesting things, if you can apply your method to maybe the practical, the real life application, a lot of researches or a lot of journals might not consider when you apply the method to solve the regression model, because the regression model is just an ordinary application in which everybody can try that. But if your method, you can try to solve maybe the motion control problem. Currently, also the method has been applied to solve problem in image processing, image denoising, image processing problem. So this is one of the paper where we work on the conjugate gradient method for solving optimization method with application to COVID-19 model and robot control. So this paper has been already accepted by Advances in Differential Equation, and it's just going to be published, I think, any moment from now. So for this paper, what we did is the three-term conjugate gradient are among the efficient variant of CG method. We have a lot of CG method. We have the hybrid CG method. We have the spectral CG method. We have other classes of conjugate gradient, but these all are modification of the main conjugate gradient method. Why the conjugate gradient method is being considered is because of its simplicity and its low memory requirement compared to other type of method, which is the Newton method or the steepest descent method. This CG method has a low memory requirement because you don't need to compute for the Jacobian matrix. You don't need to compute for the Hessian matrix. What you just need for the conjugate gradient method is just the gradient. That is why it is called conjugate gradient method. On the other hand, regression method is a statistical analysis I have explained. In this paper, we propose a modification of conjugate gradient method for unconstrained optimization model and establish global convergence under inexact line search. For the line search, it's when you propose a conjugate gradient method, you have to consider what type of line search do you want to use, because for conjugate gradient method, you will be given a function minimize f of s is equal to minimize f of s, where s is a function in Rn, F is a smooth function which is continuously differentiable. The function must be continuously differentiable and the gradient must exist. So problem of the form can be traced to, this problem has a lot of application in social sciences, engineering. As you can see, we apply this method to solve a robotic control problem. Also, the nonlinear, the conjugate gradient method of this form is an iterative method of this form, where you have f of sk plus 1, that is the current iterate. If you want to compute the current iterate, you have to already have a previous iterate, which is sk, and you have sk. That is xk, you have sk. The sk is equal to tk plus dk. The tk here is the side direction. And for conjugate gradient method, we have the exact and inexact line search. The exact line search, when you use, you're going to have the exact solution to that problem. But when you use the inexact line search, you're going to have an approximate solution to the given problem. But the most researchers, even the inexact line search is a bit difficult, but mostly researchers prefer to use the inexact line search, because for the exact line search is just one. While for inexact line search, we have different type of inexact line search. We have the a major line search, we have the strong warp line search, we have the weak warp line search. So it depends on you. Which one do you want to use? Your method can, maybe when you try your method using one of the inexact line search, it might work. And you try the method for another inexact line search, and the result might not be really favorable. So you have to try to check which of the inexact line search. And this all depends on the proof. Because if you have a method, you propose a conjugate gradient method, you have to check if this method is convergent. You have to check the global convergence of this method. And to prove the global convergence of any given method, you have to consider the inexact line search, because it has to do with decay. First, you have to check if the method satisfies the sufficient descent condition. One of the important methods, because if you submit, you propose a method and you submit, let me say, you wrote an article and submit the journal, some of the rejection has to be what type of method, what type of line search do you use when proving the global convergence. And this line search you use to prove the global convergence is the same line search you're going to use when you are running your numerical approach. You're not going to use, let me say, you use the strong line search to prove the global convergence, but when you try to run the numerical method, numerical experiment of your proposed method, because the maybe strong warp line search does not favor your proposed method, maybe then you want to go and try and use maybe the exact line search, or you want to modify the using the maybe weak warp line search. If you use the strong warp line search to prove the global convergence, so when you want to run the numerical experiment of your method, you have to use the strong warp line search. And also, for each method, let me say for this method, we use our modification is based on PRP method. PRP is one of the classical and most efficient method proposed for solving unconstrained optimization. This method was given by Pollack and Riveri, and they use this method to solve unconstrained optimization. So after this, there are a lot of methods that follows from this. We have the FR method, the Fletcher and Rives. We have the HS, we have the CD, which is conjugate descent. We have the DY, di-ion. We have the LS, which is Liu and Story. These are all modifications that follows from the classical conjugate gradient method. But even after these modifications, then there are a lot of modifications, because these methods are just the main conjugate gradient method. Then after this, we have the spectral conjugate method. We have the hybrid. The hybrid method is you're going to take, maybe you have the LS, you have the PRP. The LS and the PRP method are two methods. They have almost the same properties, because both of these methods, they are able to perform the restart. They have the restart condition, and the performance of PRP and LS method are almost similar. So let me say I take the PRP and I take the LS method. I try to combine, maybe take the maximum or minimum of this method. So when I do this, the result definitely cannot be the same as PRP or LS. So this is going to be a new result. It's going to be a new method. So this is going to be a new result. Then I can try to probe, okay, let me probe the global convergence. What approach do I want to use? Maybe I want to submit as a conference paper, so maybe I want to use the exact, because exact line sight is obvious. If you have a method, you use exact line sight, probably it's going to, most of the method will converge. So it's obvious. If you write an article using an exact line sight, and probably you're sending to maybe impact factor journal, that method, that paper, the journal will not really based on reviewers, but method proof using exact line sight are really not really considered. So you have to use one of the inexact line sight, which because the proving has to be very technical, using the either Amigo or standard wave line sight. For this method, you see, we consider the strong wave line sight. So this is a problem you are solving. This is an iterative method of the CG method. You have SK plus 1 is equal to SK plus SK. SK is the previous iterate. SK here is equal to TK plus DK. TK is the side direction, and TK is the step size, while DK is the side direction. For when X is equal to 0, our side direction D0 is equal to negative D0. So if you use the conjugate gradient method, when you have this, then you have this is the steepest descent method. If D0 is equal to minus D0, then you have the steepest descent method. But for K greater than or equal to 1, then the side direction is going to be dk is equal to negative gradient plus beta k dk minus 1. Dk minus 1 is the previous direction, while beta k is our conjugate gradient coefficient. This beta k is what differentiates all type of conjugate gradient method, either the hybrid or the spectral or the three-term conjugate gradient method. They are being differentiated by this conjugate gradient coefficient, which is beta k. So for the conjugate gradient method, when you come with, you propose a new method, all has to do with this beta k, which is going to be the conjugate gradient parameter, where beta k is known as the CG coefficient or parameter, who's different from determining different CG method. So for the line sight, which is the dk, tk, this is the exact line sight, which is f of sk plus dk. This is alpha k, which is equal to minimum of k greater than 0 of f of sk plus dk. While for the standard line sight, we have this is the standard wave line sight. Why, if you want to have the strong wave line sight, this is the strong wave line sight. The difference between the standard wave line sight and the strong wave line sight is here you have the equation 1.5, here you have 1.6. Why for the strong wave line sight, it maintains this equation 1.5, but modified the equation 1.6 to have this. If you can check, there is a bit similarity between 1.6 and 1.7. So that's why this is the standard wave line sight. Why this is the strong wave line sight. This is standard wave and this is strong wave line sight. And it's our psi k and sigma k is within this interval, 0 less or equal to psi k less or equal to sigma, which is less or equal to 1. So presently there are several types of conjugate gradient method. As I said, we have the HS, one of the classical conjugate gradient method are classified into two. We have the HS, we have the PRP, and we have the LS. Why we have the HS, which is Hitson and Stiffer. We have the PRP, which is Pollack and Revive. The last one we have the FR, which is Fletcher and Reeves. These are the first class of the conjugate gradient method. Then after them, we have some other modification, which includes the LS, Liu and Story. We have the conjugate descent method, while we have the last one is Dye and Young. These two methods are being classified based on the first type of conjugate gradient, which is the first class, is the PRP, HS, and FR. These are known as the strongest type of conjugate gradient method. So most of the modifications are being followed from this type of conjugate gradient method. So whichever method you took when you want to make your modification, you have to compare when you want to, because when you are presenting your result, there has to be a comparison with one of the existing methods. So if my proposed method is based on the PRP method, I have to compare maybe with consider the PRP method and consider maybe a similar method close to PRP method. So, but the PRP method is known as the classical and efficient CG method available for solving unconstrained optimization. However, There are a lot of people that will ask, then if this is an efficient method, why do we need to modify? Yeah, the PRP methods still are yet to be proved. The global convergence of this method are yet to be proved under other line searches. And also, when you want to run the numerical experiment, we have different 1,000 type of test function, test problem that you have to check the efficiency, the robustness of your method. So there are a lot of problems when you use the PRP method. The method might not converge. The method might fail to solve that certain type of problem. So in this case, you need to modify a method. Maybe what is the difference? When you read the PRP method, you will notice why is the PRP method failing to solve this problem? Then why do I need to modify this problem? Why do I need to modify this problem? Then you consider the drawback of the PRP method that maybe it's based on the side direction. Okay, I need to present maybe a hybrid method, or I need to present a three-term conjugate gradient method. So recently, Rivail et al., this is also one of the classical methods that follows from PRP. If you can check for PRP method, we have GK transpose YK minus 1. Our YK here is GK minus GK minus 1. That is the gradient minus previous gradient. Y here is norm of GK minus 1. That is the norm of previous gradient squared. Rivail et al. In 2012 came up with a method. So instead of GK, the denominator GK minus 1, Rivail et al. Proposed the DK minus 1, which is the previous direction. The PRP used the previous gradient, while Rivail et al. Used the previous direction. And the global convergence of this method was very good. And the numerical performance also has been very good. So this modification, a lot of modification follows from this Rivail et al. However, recently there is a researcher which is dying because Rivail et al. Proved the global convergence of this method based on exact and inexact line search, and also presented the numerical method and compare with PRP because his method is based on PRP. However, in 2016, she commented on the global convergence of Rivail et al. There is an inequality which Rivail et al. Presented. However, in 2006, she showed that there is an error in that inequality. There is what Rivail et al. Did, which it's supposed to be, and that really affected the global convergence proof. So she corrected that and made a comment, and she proposed a method. Everything she ran the result based on the Rivail. It's just that the inequality he used when proving the global convergence of the method was wrong. And she corrected it and proved the otherwise. Then compare her method with the Rivail et al. The performance of both methods are almost similar, but the only thing is that the global convergence, there was an error in the global convergence by Rivail et al., which she corrected. So currently, a lot of researchers worked on that using her approach because thousands of researchers have already used the Rivail et al. Method to propose different type of conjugate gradient method. Then 5 years after that, then she noticed that there is even an error in the global convergence proof. So that means a lot of researches that has been proposed or have been proved. That is also there are a lot of research, there are a lot of errors in many of the methods that follows from Rivail et al. So recently, a lot of researches, then she proved it because Rivail et al. Proved this under the exact line search. Then recently, Yusuf et al. Proved this method under the strong gov line search. Then a lot of researches follows from this. In our research, then we consider what this Dai et al. Did. That is based on her correction of the global convergence of the Rivail et al. Then we propose. They propose a normal CG method, but we propose a three-term conjugate gradient method. Three-term conjugate gradient method is one of the efficient variant of the CG method for solving unconstrained optimization. The only difference from the CG method is the side direction. For the side direction of the normal CG method, you have dk is equal to minus gradient plus beta k dk minus 1. While for the three-term conjugate gradient method, you're going to add another parameter at the end. When you add another parameter at the end, then you're going to have a different side direction. So the difference between all these conjugate gradient methods, the spectra, the hybrid, and the normal conjugate gradient method, it has to go with the side direction. So this is what we added. based on the method of die and all, and we prove the global convergence of the method. So this is our method. So this is our method. We come up with method like this. dk is equal to this. For the when k is equal to 0, we have the steepest descent direction. But when k is greater than or equal to 1, we define our dk to be equal to negative gradient plus beta k dk minus 1, and we have this parameter. This parameter here is defined as this, and we presented our algorithm in this form. You are given x naught in Rn, d naught is equal to d naught. This is a normal CG method. The only difference is when you have what type of side direction you use, what type of step size you use, and what type of conjugate gradient you use. But other procedures follows from the same. But the most important thing is proving the global convergence. These are just two important assumptions. Whenever you want to prove a global convergence of any CG method, you have to consider these two assumptions. Though different proof of the conjugate gradient method, it might be, the assumption might not be exactly the same. But for this method, this is the approach we use. We consider these two assumptions to prove the global convergence of the proposed method. So the global convergence of our method, this is our global convergence. One important thing I said is when you propose a method, the side direction has to be a descent direction. That is just the first most important thing about conjugate gradient method. If the side direction is not a descent direction, then there's a problem with the method. You have to modify your method whereby the side direction has to be a descent direction. That is the first property of the conjugate gradient method. If your side direction is a descent direction, then the next you prove the global convergence of the method. So for our method, we consider the strong upline side, and this is the proof of the method. We use this approach, and at the end, we obtain this. So by using the same argument as in case 1, we obtain CJ, and this is complete. But when you prove the global convergence of your proposed method, that is not the end. You cannot just prove the global convergence and submit for publication. Then you have to check the numerical performance. Just like you cannot check only numerical performance and you submit to a journal. You have to check the convergence of the proposed method. If the method is convergent, then you have to check the robustness. The robustness is how efficient is the method in solving unconstrained optimization. This all depends on you. Some researchers, maybe you consider we have a lot of test problems. So it depends on how many test problems. If I decide to submit my article to maybe IEEE or the +1, then related articles related to my work, I have to consider how many, the number of test functions they use to test the efficiency and robustness of the proposed method. For this, our method, we considered, I think, we considered 104 test problems. And this is from the test problem, you can see, this is the problem. We have the extended white and hot, and this is the dimension. This is one important thing because the dimension, this is the number of dimensions. The proposed method can be able to solve problem of even 50,000 dimensions, even 100,000 dimensions. So this is one important thing, and this is initial point. For the initial point, when solving the problem, you have to consider what initial point, because each problem, let me say I picked the extended white horse. Then I took my initial point to be 0 and 3. When I solve using 0 and 3, maybe what I'm going to get, the result might not be favorable. So I have to check other initial points, then compare the method with other existing methods. So you see, this is our proposed method. No, this is the RMIL. This is the main revive method. This is RMIL plus. This is the method by dianion. This is PRP method. If you can see, RMIL is a modification of PRP, while RMIL plus is a modification of RMIL method.
Ibrahim, you have 5 minutes more to finish your presentation.
Yeah, I'm already done, just numerical result.
Okay.
So this is just an example of the results. This is the PRP method. This is the RMIL method, and this is the proposed method. You can see when you check the number, because when you're checking, you have to check the number of iterations and the CPU time and the function evaluation. You have to compare your performance based on the number of iterations, CPU time, and function evaluation. So, and after that, if you obtain your numerical result, you have to present your numerical result in a graphical form. So this is you can use a performance profile. This is a performance profile proposed by Dolan and Moore. This performance profile, when you have your numerical result, you input your numerical result using the MATLAB, is going to present your method in graphical form. In this case, you can see this is our 3-time RMIL plus method. This is 3-time RMIL. This is a method proposed by other researchers. This is the PRP, the classical method. This is the RMIL, a modification of the PRP method. This is RMIL plus, a modification of this method. So from this graph, this is our method. You can see our method is more efficient compared to this method, because the method whose graph is above other methods is considered more efficient compared to other methods. But the most important thing is the application. Recently, as I said, a lot of application has been. This is, I think, a researcher from China applied conjugate gradient method to the, okay, this is the parameterized. Let me go, okay. Apply the CG method to solve robotic motion control problem. So I think we contacted him based on his idea, and we collaborated with him, and we came up with how he used his the method he used, how he imputed his data to the motion control problem. So, and this is the graph. When we use our method to present in the motion control, we obtain this method. So our method was able to solve problem in robotic motion control. So as I said, recently, this is on unconstrained optimization method. But recently, there are a lot of research on nonlinear problem. The nonlinear problem is more researchable now, because for the nonlinear problem, now you can apply the derivative-free approach. You can apply derivative-free approach for nonlinear, apply the derivative-free approach on conjugate gradient method for solving the nonlinear problem. And there are a lot of applications, real-life application, which that can be worked. So in case there is any researchers, anyone interested in working in this area, which is the conjugate gradient method, is either under unconstrained optimization method or not only under unconstrained optimization method. Also, if there is anyone interested in the nonlinear problem, I think you can contact me. You can get my contact, because I'm also in the research group, the faculty research group. So you can also communicate with me through that, because the most important thing is we're going to work on collaboration and publication. That's one of the ideal purpose of opening the group. And currently, we're going to work. There are a lot of advances. There are a lot of approaches that can be. There are a lot of modifications that can be done on the conjugate gradient method. There are a lot of conjugate gradient methods available, so we can if there is anyone that is interested in this area, you are welcome. You can contact me. My number is on the Telegram group. So I think, Doctor, that's all from me.
Okay. Thank you, Dr. Ibrahim, for your nice
any questions, I'm available. Welcome.
Yeah, does anyone have any question? So you may ask directly, or you can type on the chat. Any question? I have question, Dr. Ibrahim.
Okay.
So what I understand is CG conjugate gradient method. The final or the overall objective is we want to find the good performance of the model, right?
Yeah, the group performance and global convergence. The proof
Okay.
of the global convergence.
Okay, so it becomes that you need to find the solution which is satisfy the model, right? So
Yeah.
may I know what criteria or what guideline that you will use when we say that the solution is good? When we say that solution is satisfied, so what is the guideline that we can say that? Or what the criteria?
Okay. 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 First, the guideline is the global convergence. Okay, let me share. First, for any CG method, the first thing you consider is the proof, the global convergence proof. The first is the first for the global convergence proof, you have to consider the sufficient descent condition. There is a theorem, there is a lemma about the sufficient descent condition. So if you have your method, the sufficient descent condition, let me check. Okay, this is a paper on the nonlinear problem also. Sufficient descent condition. Okay, if you can see, can you see? So you can see this lemma 3.2. Suppose dk is the side direction because your proposed method has to be on the side direction. You know, in the side direction, that's where you have your conjugate gradient parameter, which is beta k. So suppose it's side direction defined by this. This is defined by your proposed method. So then dk satisfies the sufficient descent condition. So this is the sufficient descent condition. That if you have your side direction, can you show that your side direction satisfies this condition? That is one important thing. If you can prove that your proposed method satisfies this condition, then your method satisfies the sufficient descent condition. Then, based on what type of line search, exact line search, the strong verb, the standard verb line search, which approach do you want to use to prove the global convergence? Then that is another. And for the global convergence proof also, you have a lemma, you have a theorem. So is your method will your method able to satisfy the proof of that theorem or lemma? You have to give a lemma. So when you have a lemma, then you have to prove. Is your method able to satisfy that proof? Will your method be convergence? Will your method converge in that using that side direction you consider? You have your proposed method. I told you one of the important things in the global convergence is the side direction and the step size, which is the line search. So the line search you use depends, and the proof of the global convergence depends on the line search you approach. So is your method able to converge using that line search? As I told you, the classical FR method the method is still unable to be proved under certain line search because all researchers apply different line search on that PRP method, but there are certain line searches in which the PRP method are unable to converge. So then what are we going to do? Because PRP failed to converge, then they modify the PRP method. So one of the modification is somebody took the maximum of 0 and PRP method. And with that approach, he was able to prove the global convergence using that exact line search in which the PRP failed to converge. Then, if you are able to, okay, your method now is able to converge. Then the next thing is to check, because only the theoretical approach cannot guarantee the efficiency of a method. So it cannot guarantee the efficiency of a method. So then now you have to check the performance based on certain benchmark problem. You have a lot of benchmark problem. You consider, okay, your question is how do you, okay, I have a PRP method. I compare my method. My method can be able to solve this problem, and PRP method failed in the numerical performance. It failed. And there are criteria, there's a defined criteria that you consider why is the method failed. Maybe if the number of iterations exceed 1,000, or maybe if the method is failed, because sometimes when you input the method in MATLAB and you run the proposed method, it can take normally in less than 2 minutes, you will be able to have your solution, the number of iterations, function evaluation, and the CPU time. But if you input your value and you run using your initial point, then you use your, maybe, let me say I take the PRP method. After I use my initial point, I run using the PRP method. Then this method might take maybe more than 5 minutes and it's still running. I have to terminate that because the PRP method failed to solve that problem because it's taking more time. But this condition has to be defined. In your results section, you have to define why. How do you consider the failure? Okay, when number of iterations exceed 1,000, and when the method failed to solve certain problem, then it is considered that method failed to solve problem. So you have a lot of problems, even though they will be able to solve other problems, but they might also fail to solve certain problems. Also, your method might even fail to solve other problems, but based on the numerical performance, you can check maybe your method is able to solve maybe 98% of the problem, while other methods are able to solve maybe 80%. Even we have some, like the PRP method is very slow. So the performance of PRP method is very slow when solving problems. So when comparing, if your modification is not based on FR method, if it's not based on FR method, you are not even advised to use, because every method is always superior to FR method. But if your method is able to compete with the PRP method, and even the performance is more than PRP method, then you can consider your method efficient. But if your method is able to solve 100% of the test problem method you consider, then your method is robust compared to the PRP method.
Okay, it's clear now. Thank
Okay.
you, Dr. Ibrahim. So I think we need to stop here because we already reached 1 hour, because our session is only 1 hour. So thank you very much again, Dr. Ibrahim, on behalf of faculty. Thank you again. So inshallah, we will see in the next session. We can invite you in the next session, inshallah. Okay, before we... Sorry?
Yeah, sorry for that delay we had. Maybe next time I need to set my everything ready, because actually I just currently I just traveled today to Unisa. I came to Terengganu, so yeah, it's a bit before I came in, so it was a bit late. I have to set, and so really sorry for the delay it took in preparing the process.
It's
but hopefully,
okay.
maybe if I'm invited next time, I'm going to prepare before time.
Yeah. Thank you so much, Dr. Ibrahim. Okay, so I think this is the end. So I will end here. So let's recite Tajbih Kafarah and Surah Al-Asr.
Okay.
Okay, once again, thank you, Dr. Ibrahim and all. Okay, Assalamualaikum warahmatullahi wabarakatuh.
Wa alaikum salam.